Welcome to another episode of Management Unplugged by GR. Have you ever felt like you could look into a crystal ball for your business? You know, a way to peek into the future, maybe anticipate market shifts, or even just understand why certain trends are playing out the way they are. If not, well, you're about to feel a lot closer to that kind of insight. Today, we're embarking on a deep dive into the fascinating world of data, specifically how it empowers you to predict and truly understand the dynamics of business trends.
Yeah, that's exactly right.
Our mission here is always to cut through the overwhelming noise, all that information overload, and distill it down. We want to give you the essential knowledge you need to be genuinely well-informed without feeling swamped or bogged down by, jargon.
And today, our focus is squarely on uncovering and actually quantifying those hidden relationships, the ones that exist between different aspects of your business. Think about those nagging hunches you probably have. Does increasing your advertising budget really boost sales? Or, when you raise prices, how much does demand actually dip? These aren't just abstract questions, are they?
No, not at all. They're core strategy stuff.
Exactly. They're at the heart of strategic decision-making. So this deep dive is all about something called simple regression. It's a foundational concept that acts like a powerful lens, helping you clearly see, measure, and then leverage those connections to answer precisely those kinds of questions.
Absolutely. So consider this our journey into becoming, let's say, master data detectives.
I like that.
We're going to start by really unpacking the core idea of using data to make predictions, moving from just observing to genuine foresight. Then we'll dive into the intriguing challenge of finding that perfect fit within your raw data, the line that truly tells your story. We'll learn how to measure the strength of these relationships, giving us a reliable kind of relationship score. And perhaps most crucially, we'll arm you with the knowledge to avoid some extremely common yet often disastrous pitfalls, the kind that can lead to big, costly mistakes.
Crucial point.
So fasten your seatbelts. Despite the focus on data, we promise this will be engaging, clear, and maybe even a bit fun. Let's get our magnifying glasses ready and begin.
Let's do it.
Okay, let's unpack this core concept then. Simple regression. Imagine you are indeed that data detective, tasked with solving a critical business mystery. Perhaps you're trying to figure out precisely why your company's sales are either soaring unexpectedly or maybe inexplicably sinking.
Right, the classic what's going on scenario.
Exactly. And you have a strong hunch, a working theory, that sales are directly tied to your advertising spend. Simple regression, in this scenario, becomes your most indispensable tool. It's like your magnifying glass, your notebook, and your analytical mind all rolled into one. It's the method that helps you draw a clear, straight line, a quantifiable connection between those two things, advertising and sales. At its heart, simple regression is this powerful statistical technique designed specifically for forecasters and decision makers.
Yeah.
Its core purpose is to help us understand and critically predict the behavior of one variable, what we call the outcome, or dependent variable, universally known as Y, based on the changes we see in another single variable. That's the explanatory or independent variable, which we always call X.
And what's truly fascinating here isn't just the apparent simplicity, but the profound shift in perspective it offers. It moves us beyond just observing what happened. Oh, sales went up last quarter.
Right, the reactive view.
Exactly. It moves us to actively constructing an explanatory model. With simple regression, you're not just saying sales went up. You're aiming to articulate why they went up. You're trying to say something like, sales went up because advertising spending increased by, this specific amount on average.
Getting to the because.
Precisely. That transition from passive observation to actively understanding and quantifying influence is, it's an absolutely critical leap for any business looking to move beyond guesswork and into strategic, data-driven action. It lets you transform that raw data into actionable intelligence.
And what's really compelling is just how universally applicable this idea is. We encounter countless real-world scenarios where simple regression can provide these invaluable insights. The classic example, the one many of us instinctively grasp, is that connection between sales and advertising.
The go-to example.
Yeah. Can you predict a company's monthly or quarterly sales, that's our Y variable, by simply looking at how much it spends on advertising, our X variable, during that same period? It's not just about knowing if there's a link, but actually quantifying it. How strong is it?
Exactly. And beyond marketing, think about the automotive industry. Predicting the price of a used vehicle, RY, very often depends heavily on its mileage, which would be RX.
Right, makes sense.
Intuitively, we all know higher mileage usually means a lower price. But simple regression allows us to put a precise number on that depreciation per mile on average.
Right.
Or think about time series data, which is everywhere in business. How do changes in the world pulp price, RX, influence the volume of pulp shipments, RY? That negative relationship we often observe between price and quantity becomes explicitly clear with regression.
So price goes up, shipments go down.
Generally, yes, and regression tells you by how much. Even simpler, imagine trying to predict your sales, Y, based purely on the passage of time, X, maybe looking at sales figures month after month. You could plot this on a scatter plot, time on the horizontal axis, and simple regression will draw that trend line right through it, quantifying the average growth or decline over that period.
Got it.
So in all these diverse cases, the overarching goal is the same. Build a robust, quantifiable relationship, a model that not only enhances our understanding of how different business factors interact, but also enables us to conduct meaningful experiments and ultimately achieve far more accurate forecasts.
So to circle back on that, understanding is really key here. It's about gaining a deeper, more granular insight into how different factors within your business environment interact and influence each other. That move from just raw numbers to actionable understanding is, well, that's where the magic happens, right?
Absolutely.
And once you have that understanding, you unlock the ability to truly experiment. We're talking about what-if scenarios, but with real data behind them.
Right, not just guessing.
Exactly. What if we increased our advertising spend by 10% next quarter? How might our sales respond based on the historical patterns we've quantified? This isn't just theory. It's a powerful framework that allows you to influence your future outcomes through present, informed decisions. It helps shift your business from being reactive to proactive.
A crucial shift.
And of course, the ultimate tangible benefit is vastly improved accuracy in your predictions. By leveraging the demonstrable influence of related variables, your forecasts become sharper, more reliable, and ultimately more valuable for guiding your strategic choices.
Makes sense.
So at its most fundamental level, simple regression involves analyzing pairs of observations, like a sales figure, Y, for a specific advertising spend. Our detective's task is to find the best linear relationship that describes this pattern, Y equals A plus B times X plus E.
Okay, let's break that down.
Right. So A is the intercept, the starting point of our line. It tells us the average value of Y when X is 0. B is the slope, indicating how much Y changes, on average, for every 1 unit change in X.
The rate of change.
Precisely. And that little E at the end, that's the error or residual. It's the unavoidable deviation, the part of the outcome that our model simply can't perfectly explain. Every good detective knows there are always a few lingering questions, right?
Always. So once you've gathered these pairs of observations, let's stick with your sales and advertising data example, and you visualize them on a scatter plot, you'll see this cloud of points across the graph.
Yeah, often looks messy.
It can, yeah. And the immediate challenge, as you brilliantly highlighted, is how do you draw the best straight line through these points? It's not just about eyeballing it. It's about finding the one line that most accurately represents the underlying trend.
Yeah.
And here's where that term best fit takes on a very specific mathematical meaning. It's not just a casual expression, it's the result of a precise objective, which, immediately raises a crucial question for our data detective work. How do we quantitatively, objectively decide which line truly captures the essence of this data? How do we distinguish it from all the other possible lines we could draw?
That's a great question. And it's where this idea of errors comes into play, isn't it? Think of it like this. Imagine you're trying to draw that perfect straight line through a bunch of scattered crumbs on a table.
Okay, I'm visualizing crumbs.
Some crumbs are very close to your line, others are quite far away. For each individual crumb or data point, the error is simply the vertical distance between where the crumb actually is, its observed Y value, and where your line predicted it would be, its Y hat high value.
The predicted value on the line.
Exactly. These errors, which we formally call residuals, represent all the parts of the outcome that your carefully drawn line doesn't perfectly explain. They're the little mysteries, the deviations that your current model couldn't quite account for.
Okay, residuals are the unexplained bits. So, to find that optimal best fit line, the one that minimizes these mysteries, we use a technique called ordinary least squares, or OLS.
OLS. Sounds technical.
It sounds technical, but the core concept behind least squares is actually quite intuitive once you grasp it. We want to find the line that generates the smallest total amount of wrongness.
Okay, minimize the wrongness. I like that.
Now, simply adding up those errors, those residuals, won't work. Why? Because some errors will be positive, the actual point is above the line, and some will be negative, the point is below the line. If you just add them, they'd cancel each other out, potentially giving you a sum of 0, even if your line is terrible.
Ah, right. The positives and negatives would balance out.
Exactly. So what we do is we square each error first. Squaring does two crucial things. First, it makes all the errors positive, so they don't cancel out anymore. And perhaps more importantly, it significantly penalizes larger errors.
How so?
Well, think about it. An error of 1 when squared is still just 1, but an error of 10 when squared becomes 100. This mathematical choice means our best fit line is the one that works hardest to minimize those biggest deviations. It ensures the line isn't just casually off, but genuinely close to the majority of your data points.
I see. So squaring gives more weight to the really far off point.
Precisely. Once all errors are squared, you sum them up. And the line that gives you the smallest sum of squared errors is, by definition, your best fit line.
It's a bit like maybe a quality control manager trying to find the most efficient path through a factory floor. You want to minimize the collective stray steps everyone takes.
That's a decent analogy, yeah.
Squaring the deviations means we treat being a little off just as seriously, whether you're too high or too low, and it really penalizes being way off. It pushes the line to be as central and representative as possible.
That's a good way to put it.
And the truly great news for all of us data detectives is that while the underlying math for calculating the slope and the intercept is precise, well, no one, absolutely no one, does this by hand anymore.
Thankfully.
Yeah. Software, whether it's a sophisticated statistics package or even just a common spreadsheet program like Excel, handles these complex computations instantly. It gives you that best fit line in seconds.
Precisely. Let's look at some real applications. For instance, consider sales data observed over 10 distinct time periods. If you plot sales Y against time X, the OLS method might give you an equation like Y equals 23.33 plus 3.39X.
Okay, what does that tell me?
This equation is incredibly practical. It tells us that, on average, for every single unit of time that passes maybe a month or a quarter, your sales tend to increase by 3.39 units. And that's starting from an estimated base sales figure of 23.33 units when time is at its initial point, when X is 0.
So a clear growth trend quantified.
Exactly. It's not just a number, it's a quantifiable insight into your sales growth trajectory. A marketing manager could use this to project future sales under current conditions, or a production manager could anticipate increased demand based on this trend.
That's a clear upward trend. But what if the relationship is different, like that pulp example you mentioned earlier?
Right. Consider pulp shipments, S, related to world pulp price, P. Here, the relationship derived through least squares might be something like S equals 71.7.075p.
Okay, I see a minus sign there.
Exactly. What immediately jumps out here is the negative slope, that negative 0.075. This is a critical piece of business insight. It tells you that, on average, for every $1 increase in the world pulp price, pulp shipments tend to decrease by about 0.075 units. If our units were in millions of metric tons, that translates to 75,000 metric tons less shipment volume per dollar increase.
Wow, okay, that's very specific.
It is, and incredibly actionable for someone in procurement or sales. If you're a buyer, you know higher prices typically mean less supply available. If you're a seller, you understand how price increases might impact your sales volume. It quantifies that inverse relationship we often expect in markets.
So connecting this back to the big picture, finding this best fit line isn't just about drawing something on a graph.
Not at all. It's about quantifying a crucial business relationship. It tells you not only if two things move together, but how much they move together on average. That slope, that's the actionable insight.
Right.
For instance, if you're a marketing manager and you discover that, say, a 1% increase in ad spend leads to an average 3% increase in sales, that's not just an interesting stat. It's a direct, measurable lever for budget allocation and strategic planning.
Yeah.
Or if you're in operations and your analysis shows that a slight dip in raw material price directly correlates with a quantifiable surge in demand for your final product, you can proactively adjust your inventory and production strategies to capture that opportunity. These aren't just academic numbers. They're direct inputs for shaping your business's future.
Okay, so our data detective work has given us this best fit line, showing the average relationship. But, Any good detective knows averages can be misleading without context. How strong is that relationship really? Even with a line drawn, how closely do those individual data points actually cluster around it?
Excellent question. This is where our next crucial tool comes in. The correlation coefficient, usually denoted as R. Think of R as a precise relationship score. It's a numerical grade that tells us both the strength and the direction of the linear connection between our two variables, x and y. And the score always falls within a specific range, from -1, all the way up to +1, +1.
-1 to +1. Got it.
The sign of R is our first clue. It tells us the direction of the relationship. If R is positive, greater than 0, we have a positive correlation.
Meaning they move together.
Exactly. As one variable tends to increase, the other variable also tends to increase. They move in the same direction. A perfect positive correlation, where R plus 1 means all your data points fall precisely on an upward sloping straight line. A classic intuitive example is ice cream sales and temperature. As the temperature rises, ice cream sales predictably tend to increase.
Makes sense. Warmer weather, more ice cream.
Conversely, if R is negative, less than 0, we're looking at a negative correlation. This indicates that when one variable increases, the other tends to decrease. They move in opposite directions.
Like your pulp price and shipments example.
Precisely. As world pulp price climbs, the quantity shipped tends to fall. A perfect negative correlation, where R equals -1, means all points lie exactly on a downward sloping straight line. And if R is approximately 0, say very close to 0, it means there's no discernible linear relationship between the variables.
So they're independent.
Well, they appear to move independently, at least in a straight line fashion. There might be a nonlinear relationship, but R won't capture that.
Ah, okay. Important distinction.
Very. Beyond direction, the absolute value of R, just the number, ignoring the plus or minus sign, tells us the strength of the relationship.
How close the points are to the line.
Exactly. If the absolute value of R is closer to 1, either +1 or -1, it indicates a very strong linear relationship. The data points will hug the regression line very tightly, showing a clear, consistent connection. This means our detective's prediction based on X will be quite reliable for Y.
And if it's closer to 0?
If the absolute value of R is closer to 0, it signals a weak or even non-existent linear relationship. The data points will be scattered widely, far from the line, implying that changes in X are not a strong predictor of changes in Y. A correlation of, say, 0.2 suggests a very weak linear link, while 0.8 suggests a strong one.
Let's ground this with our earlier examples again. For the sales and time data, you said the correlation coefficient R was 0.735.
That's right.
So that indicates a moderately strong positive relationship. It tells our detective that as time went on, sales generally increased. And while the trend was clear, it wasn't perfectly predictable month to month. There were still other factors at play, but time was a significant contributor.
Correct. Now, compare that to the pulp price and shipments data, where R was a much stronger -0.931.
Very close to -1.
Exactly. This signifies a very robust negative relationship. It implies that a higher price almost consistently meant significantly lower shipments. That gives decision makers a high degree of confidence in how price changes would likely affect supply or volume.
Okay, our sounds incredibly useful.
It is. The correlation coefficient is undeniably a valuable measure for our detective work. However, and this is a big however, there are crucial cautions we must observe to avoid misinterpreting its findings.
Ah, the pitfalls.
Yes. First, and this is absolutely critical, our only measures linear association. It's designed purely to detect straight-line relationships.
Okay, you mentioned this. So if it's curved,
it fails. Here's where it gets really insightful and potentially really misleading if we're not careful. Imagine our dating analogy again. If someone asks, "Are you two related?" You want to know if there's a strong, clear, direct connection, right? Not just a casual acquaintance.
Right.
The value tells you that, but only if they're metaphorically holding hands in a perfectly straight line. If the true relationship between your variables is curved, maybe U-shaped, or any other nonlinear pattern, the correlation coefficient can actually be very close to 0, even if there's an incredibly strong nonlinear relationship present.
Wow. Sour could be 0, but there's still a strong pattern.
Absolutely. The source material shows an illustration where data clearly forms a curved pattern, yet the calculated correlation coefficient is a measly 0.05. This demonstrates that R completely misses the boat on strong, curvilinear patterns. And those are very common in business. Think about diminishing returns, for instance.
Like more advertising helps, but only up to a point.
Exactly. Initial ad spend yields high returns, but after a certain point, additional spend yields less and less. That forms a curve. So the lesson is always, always visually inspect your data with a scatter plot first. Don't just compute R.
Okay, rule one, look at the picture. What else?
That's a vital point. Another crucial caution for our data detectives concerns sample size. The correlation coefficient R can be remarkably unreliable and unstable when you're working with only a few data points.
Small samples are tricky.
Very. If you analyze, say, only 10 observations, the calculated R value can fluctuate wildly. You might see a strong correlation, maybe close to +1 or -1, purely by random chance, even if the true underlying relationship in the larger population is only moderate or even non-existent.
Like flipping a coin 10 times and getting 8 heads.
Exactly like that. It looks like a strong bias, but it could just be a small sample size fluke. For a correlation coefficient to be reasonably stable and truly representative of a population, and for our detectives' conclusions to hold weight, you generally need at least 30 observations.
30. That's a good rule of thumb.
It is. Small samples simply don't provide enough robust evidence to confidently draw strong conclusions about the strength and direction of a relationship. Relying on an R from sparse data is like a detective declaring a case solved with only 2 blurry fingerprints, highly risky.
Okay, so R tells us direction and strength, but only for linear relationships. And we need enough data. Got it. But there's another layer to this, isn't there? How much of the variation we see in our outcome variable can actually be attributed or explained by our explanatory variable?
Yes, exactly. This brings us to another powerful statistic known as R squared, often written as R squared.
R squared. Heard of that one? Coefficient of determination.
That's the one. It sounds a bit formal, but to demystify it, think of R squared as the percentage of the story that your explanatory variable X is capable of telling about the outcome variable Y.
The percentage of the story. I like that.
If we connect this to the bigger picture, R squared provides a highly practical and intuitive measure of how much explanatory power our single independent variable X truly possesses over Y. It goes beyond just drawing a line. It tells us how much of Y's natural variability and fluctuations that relationship, can genuinely account for. It's a direct measure of the model's predictive utility.
This sounds really useful for a business person. Think of it like this. Your monthly sales numbers, or maybe stock prices, or even customer churn rates, they all bounce around from period to period.
Sure, there's always variation.
That constant movement, that unpredictability, that's what we call total variation.
Yeah.
Now, if your advertising budget, as quantified by your simple regression model, can explain, say, 70% of that bouncing around in sales, then your R-squared value would be 0.70 or 70%. The remaining 30%. Well, that's still a mystery for this particular model. It's variation that's either due to other factors not included in our simple model, or maybe just random, unexplainable chance.
That's a perfect way to explain it. More formally, R squared is the proportion of the total variation in the dependent variable Y that is explained by your regression model, specifically by the changes you observe in X. The rest is simply unexplained variation. It's like a pie chart, where R squared is the slice explained by your X variable.
And this is hard to calculate.
Actually, here's a neat mathematical link that simplifies things considerably, especially for the simple linear regression we're discussing. R squared is quite literally just the square of the correlation coefficient. It's R squared.
Oh, really? So if I have R, I just square it?
Exactly. So if you've already calculated R, you automatically have R squared right there. This direct relationship makes it very easy to transition from understanding the strength and direction of a relationship to understanding its explanatory power, R squared.
Okay, let's apply this then. For our initial sales and time data, we found R was 0.735.
Correct.
So the R-squared value is just 0.735 squared, which comes out to 0.540, or 54%.
Exact.
This tells our data detective that a substantial 54% of the observed variation in sales data can be explained by its linear relationship with the passage of time.
Huh.
That seems like a decent chunk.
It is. It gives us reasonable confidence in time as a predictor. However, it also means that the remaining 46% of the sales fluctuation is what we consider random fluctuation, or is influenced by other factors not included in our simple model, things like specific marketing campaigns, economic shifts, competitor actions, you name it.
Right, and moving to the pulp price and shipments data, and was that really strong neck is a 0.931.
Uh-huh.
The R-squared is kind of 0.931 squared, which calculates to 0.867 or 86.7%.
A much higher value.
Yeah, that indicates a much higher level of explanatory power. An impressive 86.7% of the variation in pulp shipments is directly explained by its linear relationship with the world pulp price.
Yeah. Which is a profoundly strong relationship. It suggests that price is an overwhelmingly dominant factor in determining shipment volumes in that market.
So, for anyone involved in the pulp industry, that R-squared value would immediately highlight price as a critical variable to monitor and manage. It gives immense confidence in price-based forecasts.
Absolutely. And let's introduce another compelling example. PCV sales, that's passenger car and light truck sales, and gross domestic product, or GDP.
Okay, car sales and the overall economy.
Exactly. When we examine the relationship between PCV sales, our Y variable, and the national GDP, our X variable, a regression analysis yielded an R-squared of 0.901.
Wow, 90.1%.
Remarkable, isn't it? 90.1% of the variation in PCV sales is explained by the linear relationship with GDP. That's an extremely high explanatory power, indicating that GDP is a profoundly significant, almost dominant factor in predicting PCV sales.
So for a business operating in the PCV market, such a high R-squared means that economic forecasts for GDP become incredibly valuable, almost direct predictors for their own sales targets.
Precisely. A higher R-squared generally implies a more reliable and useful model for prediction. However, and this is crucial, it's not a silver bullet.
Another however.
Always. A high R-squared doesn't automatically imply causation, nor does it guarantee the model is perfect for all scenarios or that it's even the right type of model. Which brings us neatly to our next crucial phase of detective work, checking our homework.
Checking the homework. I like it. So after you've done all that meticulous work, our data detectives isn't finished.
Not by a long shot. You've cooked up your main dish, your beautiful regression line. But what about those little bits left on the plate?
The residuals.
Exactly. Those are your errors or leftovers, formerly known as residuals, and they represent the parts of the outcome your model simply couldn't explain.
And you said earlier we want those leftovers to look, well, random.
Right.
Not like a messy pattern or some specific design.
That's exactly right. If our model is truly the best fit and accurately captures the linear relationship, then what's left over, the unexplained variance represented by the residuals, should be nothing more than random noise. It shouldn't have any hidden patterns or structure.
Okay. And how do we check for that randomness?
The most effective way for our data detective to scrutinize these leftovers is to visualize them using something called a residual plot.
A no plot.
Another plot, but this one's specifically for checking assumptions. You create a new scatter plot where you plot each residual, that vertical distance between the actual point and your line, against its corresponding explanatory variable, x.
Okay, plotting the errors against the input variable. What are we looking for?
What does a good residual plot look like? One that indicates your linear model is appropriate. It will show a completely random scatter of points, evenly distributed in a horizontal band around the zero line, with no discernible patterns whatsoever.
Just like static on an old TV.
That's a pretty good analogy, yeah. Just random noise. This random scattering confirms that your linear model has indeed captured the systematic relationship, and what's left is just pure, unpredictable error, which is exactly what we want. We saw that kind of healthy, random scatter in the sales time example and the GDP PCV example, which gives us confidence in those linear models.
But what about a bad plot?
Mm-hmm.
This is where the detective's alarm bells should ring, right?
Absolutely. If you see any discernible pattern in your residual plot, maybe it looks like a V shape, or an inverted V, or a distinct curve like a smile or a frown, or even if the spread, the variance of the points visibly increases or decreases as X changes, that's a huge red flag. It's a strong indication that a simple straight line was not the best choice for your data, or that your model is missing something important.
Like in the pulp regression example you mentioned.
Exactly. The residual plot for that pulp regression actually showed a very clear V-shaped pattern. This immediately suggested that a straightforward linear relationship was inappropriate. Such a pattern could mean there's a nonlinear relationship at play that your straight line isn't capturing. Or perhaps you've omitted a crucial variable from your model that influences the residuals in a systematic way.
So the residuals are telling you, hey, your model's not quite right.
Precisely. It's often much easier to spot these subtle yet critical issues in a residual plot than by simply looking at the original scatter plot alone. It guides our detective towards refining the model, maybe trying a different approach.
Okay, so check the residual plot for patterns. What else should our detective look for in the residuals?
Beyond overall patterns, our detective also needs to be vigilant for the odd ones out, what we technically refer to as outliers.
Ah, the outliers. The weird points.
Exactly. These are individual observations that stand significantly apart from the general pattern of the data. They exhibit unusually large residuals, meaning they are far away from the prediction line. They are data points that simply don't fit the overall linear pattern well.
Are they just mistakes, like typos?
Sometimes they are straightforward, like a simple data entry error, a misplaced decimal point maybe, which is relatively easy to spot and fix. But far more interestingly, they can represent genuinely unique, exceptional, or even groundbreaking events that deviate from the norm. And these demand closer investigation, not just deletion.
And sometimes ignoring these odd ones out can have truly profound, even disastrous consequences, right? You mentioned a story.
Yes, the Antarctic ozone hole story. It's a compelling and frankly sobering real-world example. This massive environmental crisis, which affects all life on Earth, could have been detected much, much earlier.
How so?
Well, back in the 1970s and early 80s, satellites were tirelessly collecting atmospheric data. But the automated software processing this vast amount of information was programmed to reject any extremely low ozone values recorded near the South Pole. It automatically flagged them as aberrations or outliers.
So software just threw them out.
Essentially, yes. The underlying assumption was this must be a mistake. It doesn't fit the expected pattern. It wasn't until ground-based instruments in 1985 finally confirmed a severe and widespread ozone depletion that scientists went back and revisited that ignored satellite data.
And what did they find?
They found the recorded ozone levels had actually started falling way back in 1979. If those points flagged as outliers had been investigated properly rather than just dismissed, this enormous environmental problem could have been detected and potentially addressed years sooner. It's a chilling illustration of the critical danger of simply tossing out data points that don't conform to your expectations.
Wow, that really drives the point home.
Yeah.
Sometimes the outlier is the story.
Exactly. Sometimes the error isn't in the data, but in our interpretation or our automated rules. And in our PCV sales and GDP example, the residual plot also revealed at least one and possibly three significant outliers.
And were they errors?
No, they didn't represent data entry errors. Instead, they corresponded to specific years, notably 1973 and 1974, where PCV sales were substantially less than predicted by the linear relationship with GDP alone.
What was happening then?
The first major energy crisis. Remember the oil embargo, the sharp, sudden surge in gasoline prices. These outliers weren't statistical anomalies to be discarded. They were direct indicators of external, influential macroeconomic events that profoundly impacted vehicle sales. Events which a simple linear model based solely on GDP couldn't possibly account for. They forced our detectives to look beyond the simple model and consider broader economic and geopolitical contexts.
Okay, so outliers need investigation. But you mentioned something else too, influential observations. How are they different?
Right. Influential observations. These are distinct from typical outliers. While outliers are points that don't fit the overall pattern well, they have large residuals. Influential observations are points that, if you were to remove them from your data set, would markedly change the position and slope of your entire regression line.
So taking one point out dramatically changes the line.
Yes. They usually have extreme values in your X variable, meaning they lie far away from the average X values in your data, either unusually high or unusually low. They have high leverage.
Feel rich. Okay.
The source material provides a brilliant analogy for this, calling it the King Kong effect.
King Kong. Okay, I'm listening.
Imagine for a moment you're studying the height-rate relationship for a sample of, say, 20 average gorillas. Based on this data, you might find a moderate correlation, maybe R equals 0.527, and your regression line reflects the average trend for those typical gorillas.
Makes sense.
Now, what happens if you add just one very large gorilla King Kong himself to your data set? Because this single point is so extreme in both height and weight, it possesses immense leverage. It can drastically pull your entire regression line towards it, skewing its slope and intercept. And in the process, it can massively inflate the correlation coefficient for the whole data set. That original 0.527 could, for instance, jump all the way up to a seemingly very strong 0.940.
Wow. Just one point does that.
Just one point with enough leverage, yes. That's the King Kong effect in action.
And here's the key, maybe counterintuitive distinction that makes these influential observations so tricky for our detective work. Unlike typical outliers, which have large residuals because they're far from the line, influential observations often have small residuals.
Small residuals, but they're extreme points.
Exactly. Why? Because the regression line has been forcefully pulled towards them. The line itself has sort of contorted its shape to accommodate this powerful outlying point. So they don't look off the line. They are, in a sense, dictating the line's path, making them much less obvious to spot just by looking at the size of the residuals.
Oh, that is sneaky.
Very. This is precisely why they matter so much. Influential points can create a completely misleading impression of the overall relationship within your data if they're not carefully identified and examined. They might represent a different population entirely, like King Kong versus average gorillas, or a rare exception or a unique event that heavily skews your findings and distorts the true average relationship for the majority of your data.
So a good detective doesn't just look for what's obviously wrong, large residuals, but also for what's subtly manipulating the evidence, high leverage points. Always be wary of the King Kong lurking in your data, silently dictating the story your model tells.
Okay, this is all incredibly helpful for refining the model.
Yeah.
But let's zoom out again. What does all of this mean for our data detective work in the bigger picture? This brings us to what you call the golden rule, right?
Yes, this is the absolute biggest takeaway, the golden rule, the one you should, as you said, metaphorically put on a t-shirt and internalize. Correlation is not causation.
Say it again. Correlation is not causation.
Exactly. This is the ultimate pitfall, a critical trap that trips up countless analysts and decision makers. Just because two variables are highly correlated, meaning they consistently move together, up and down in sync, absolutely unequivocally does not mean that one variable causes the other.
It seems obvious when you say it, but people fall for it all the time.
All the time. This point truly cannot be stressed enough. It's arguably the most common mistake made in data interpretation, and it can lead to potentially disastrous business decisions. And the classic example illustrates it perfectly. Suppose you run a study and discover a remarkably strong positive correlation between weekly national cola sales, our Y variable, and the weekly number of deaths by drowning, our X variable.
Cola sales and drownings.
Okay. You plot them, the line looks fantastic, the R value is high, R squared is impressive, everything looks statistically significant.
And a naive observer, perhaps someone who unfortunately skipped this particular deep dive, might immediately jump to an absurd conclusion. Aha! Drinking more cola must somehow cause drownings.
Or equally ridiculous, drowning somehow cause people to drink more cola.
Yeah.
Both conclusions are clearly illogical and, frankly, dangerous if acted upon.
Yeah, if a soft drink company believed the first, they'd be shutting down operations. If they believe the second, well, that's just dark.
It is. This raises that fundamental question for our data detective. What unseen forces, what silent puppet masters are actually at play here? The drowning and cola sales example perfectly illustrates the concept of a lurking variable.
Lurking variable. Okay.
Both cola sales and the number of drownings are indeed highly correlated, but neither directly causes the other. Instead, both are strongly influenced by a third, unobserved factor, that lurking variable. In this case, it's pretty obviously the weather, specifically the ambient temperature.
Ah, the heat.
Exactly. In the summer months, temperatures are high, so people naturally consume more cold beverages like cola. Simultaneously, more people engage in swimming and water-based activities, which sadly leads to an increase in drownings.
And in winter, both go down.
Precisely. In winter, both cola sales and drownings are significantly lower. The temperature is the underlying causal force driving the movement in both variables. It creates the illusion of a direct causal relationship where none actually exists. A business that didn't understand this distinction might waste resources trying to prevent drownings to boost cola sales, or vice versa, completely missing the true driver: seasonality and temperature.
That's a brilliant example. So always look for the lurking variable. But it's not just lurking variables, is it? You mentioned confounding, too.
Right, another tricky concept, confounding variables. This occurs when there is plausibly a causal effect you're trying to measure between X and Y, but another variable, let's call it Z, is correlated with your explanatory variable. X and Z also has its own direct causal effect on Y. This confounds or confuses your ability to isolate the specific impact of X on Y.
Okay, can you give an example?
Sure. Consider this business scenario. You're trying to determine if increased advertising expenditure, X, leads to increased new car sales, Y. It's plausible there's a direct causal link there.
Seems reasonable.
However, what if your company also has a strategy where advertising budgets are only significantly increased during periods when car prices are heavily discounted? Z.
Ah, so ads run when there's a sale on.
Exactly. In this situation, advertising expenditure X and price discounts Z are confounded. When sales increase, it becomes impossible for our detective to disentangle whether that increase is genuinely due to the compelling new ads, X, or whether it's primarily driven by the attractive lower prices, Z, or maybe some combination where both are intertwined.
Because they always happen together.
Precisely. You can't reliably isolate the individual impact of advertising because it's always moving in lockstep with price discounts in this scenario. This means any simple regression model looking only at ads and sales would likely attribute the sales increase to advertising, even if price was the true, or at least a significant, driver. The effective price is confounded with the effect of advertising.
The overwhelming takeaway here, the core lesson for every aspiring data-driven decision maker, is to always think critically. Correlation is an incredibly useful signpost. It's a hint that something interesting might be going on, a signal for our detective to investigate further.
A starting point, not an end point.
Exactly. But it is emphatically not a direct arrow pointing to causation. True data literacy means understanding the broader context of your data, actively looking for other influencing factors like lurking or confounding variables, constantly questioning the why behind the correlation, and recognizing the limitations of your models.
Absolutely. While simple regression reveals powerful relationships, knowing when those relationships are a result of genuine cause and effect versus a clever illusion created by these other variables is paramount for making truly informed, strategic, and successful business decisions.
So, to briefly recap our deep dive then, we'd explored the immense power of simple regression as a tool to understand and quantify crucial relationships within your business data.
Right. We learned the meticulous process of finding that statistically best fit line using the principle of least squares.
Minimizing the squared errors.
Exactly. And how to measure the strength and direction of these relationships with the correlation coefficient.
We also successfully demystified R-squared, understanding it as that percentage of variation in your outcome that your model can confidently explain.
And we delved into the vital importance of checking our model's homework, carefully analyzing residuals for patterns,
Looking for randomness.
spotting those quirky outliers that might be errors or crucial insights,
Investigate, don't just delete.
and being intensely wary of influential points, those King Kongs that can subtly yet powerfully skew your entire findings.
But perhaps most importantly, we've emphatically hammered home the golden rule. Correlation is not causation.
The big one. Understanding this critical distinction and recognizing the insidious roles that lurking and confounding variables can play in misleading our perceptions is perhaps the single most crucial insight for anyone looking to make genuinely smarter, more reliable decisions with data in the complex world of business.
These concepts aren't just dry statistical theories for academics in ivory towers. They are practical, empowering tools for you listening right now to become a smarter, more discerning data consumer and a more effective decision maker in your own business. They equip you with the foresight to move beyond mere hunches and truly understand what drives your outcomes. So the next time you encounter two trends moving together in seemingly perfect harmony, don't just accept it at face value. Ask yourself that critical question. Is this truly a direct cause and effect? Or is there a hidden hand, a clever lurking variable, orchestrating their synchronized dance?
Food for thought.
See you later. Bye-bye.